This video is going to help you with activity A. Make sure you read the directions very carefully. Students who don't understand how to do this gizmo or each section, they usually don't read the directions or pay attention to what it's asking or what it's telling you. So focus. Activity A says first get the gizmo ready. Click reset and turn on show grid. So reset, I already clicked it. I'm going to turn on show grid right there. This allows us to quantify, which is just a fancy way to say measure the orbit of this planet based on this gravity and this velocity that it has. So in order for us to quantify or just measure the orbit, we have to understand a couple of things. The velocity of a planet is represented by an arrow called a vector. Here is that vector, this purple here. Now the longer we make it, the more velocity, the shorter the less velocity. This is the sideways or lateral speed of the planet, and this is the gravity pulling the planet towards the center of the sun. Notice that as we make the velocity more, the arrow gets longer, but also we can change the direction of it. And as we're changing the direction, there are different numbers that are showing that direction and speed on the grid. And so I just want to point out a couple of things, help you understand this. The two components, the I component represents east to west, the J component represents north to south. So if this planet is out in space, it can go that direction or that direction. We call those west, right? East and west. Or it can go north or it can go south. It could also have a mixture, right? The planet could go in a diagonal this way, which would be something like southeast, right? Or this way, southwest, and so forth. Now, in order to track this, to measure it, to quantify it, we just have to agree on a couple of terms. This gizmo is telling us that the I component is east to west. So if a planet is going to go either to the west or east, that's going to be on the I, they're calling that I. And if it's going north to south, that's going to be J. Now notice, let's observe, on the simulation, the J component, north to south, is on the y-axis. Right, the I component, east to west, that's on the x-axis. So, for this gizmo, for this simulation, if someone were to tell us a couple of numbers, right, like on a graph, the x, y, which in this case is going to be I and j. If they told us two numbers, then we could pretty much understand where that planet is in space. And if we know where the planet is and we know its vectors, then when we change them, we can see how that affects the orbit. That's just a little bit of background here. So let's do it. It says, how do we describe the shape of an orbit? The distance unit used here is astronomical units AU. It tells us to place the planet on the I-axis at r equals negative 3I. So here's the I-axis. So we're going to put on negative 3I. And we can actually see that here, r. The planet is on negative 3I, right? 3 astronomical units from the sun. And it's negative 3 because that's going towards the west. Just a way for us to measure this. Then it tells us to move the velocity vector. Remember, the velocity vector is the arrow, this right here. The green vector, which is gravity, will change based on the position and how close the planet is to the sun. But we can change the velocity vector just by moving it. We're changing the speed. It tells us to move the velocity vector so that it is v equals negative 8j. So if we pull this down, we see that v here changes, negative 18j, too much. Now if we're watching over here, this is going to change as we move this up and down. Now notice if we get it just right, it's negative 8j. That's exactly where they want us to be on the grid. All right. Then it tells us to press play and click pause after 1 revolution. Oh. Forgot to turn on the show. You should have these show trails on from previously. One revolution is done. And then it asks us a couple of questions about it. It says that the shape of the orbit is called an ellipse. Make sure you read all of this. And it says turn on show Foci and center. Boom. Check that out. I'll turn the grid off for a second. This is the center of the orbit, and these are the two foci, and it's going to ask you a couple of questions about them. Then it's going to say to experiment, try several other combinations of initial position and velocity. That means just move the planet around, move its velocity around, and see what happens, right? If you have different combinations, different locations, different speeds, different velocities, then you can get different shapes. Just try that out and answer the questions. Now at the bottom here, this is talking about eccentricity. Make sure you read this part. The eccentricity is equal to the distance between foci divided by the total width of the ellipse. And there are no units for this. So I want you to move the planet to r is negative 5i. Remember, we can do that easily. Negative 5i, it says it right here. I actually have mine a little bit higher, so let's move that until that number is perfectly negative 5i. There it is. And it tells you to move it to negative 8 like it was before, so that's a straight down line. Let's zoom out a little bit. Notice we're at negative 12, so I'm going to move it up a little bit until it hits negative 8. Perfect. Then it tells you to press play. Now, the distance between the foci, what you're going to do is you're literally going to count the distance between these foci. How much space is between here and here? The two foci. And then you're going to count what's the distance of the total orbit from here to here. And then after reading the directions, you'll be able to calculate the eccentricity. All right? The rest is just questions that are asking you to think about different scenarios and how the ellipse or the orbit will change. Call me if you need help.